Derivative inner function. Okay, so derivative of x plus 1 over x minus 1, if we use a quotient rule like was suggested, I'll leave the x minus 1, x plus 1, it's right there. So now to take this derivative, so it's bottom times derivative of the top minus top times derivative of the bottom over bottom squared. So the top simplifies. We have x minus x, so that's gone. We have negative 1 minus 1. So the top is really just a negative 2.
Why is it shouldn't be x plus 1 squared? On the bottom?
No, I need no. Take careful. Yeah, watch out. No, it's x minus 1. It's the bottom square, right? Remember, this was after we flipped it. This was the flipped expression.
Yeah.
And then we take the derivative of original expression. The original expression has x minus 1 on the bottom.
Why do we take the derivative of the original expression out?
Chain rule. Right? I need derivative of outer function. Derivative of outer function is 1 on x. But I've got to keep inside here the
okay.
inner function. So what does that do to it? It just flips it. And I got to take the derivative. All right, so if you just, what's the top here? Negative 2, is that what we said?
Yeah.
Negative 2. There are 2 x minus 1s here, and there's an x minus 1 there. We're going to cancel one of them, right? So we're left with negative 2 over x plus 1, x minus 1. You could write it as difference of squares, but I don't think it's an advantage. Again, I said factor form is usually more advantageous in general. So we'll leave it like that.
You should use difference of squares with x minus 1 squared, right?
I did not use no, not I was saying here you could write this as x squared minus 1. You could write this final result as a difference of squares, but it's not that useful. Here, all I did was take x minus 1 away and x minus 1. I canceled these common factors.
Oh, okay.
Left a single x minus 1 here and this x plus 1 here.
Okay.
You should note that the derivative does discard the negative 1 and 1, right? It discards those endpoints there. You could not put negative 1 into the derivative or 1 into the derivative, right? The formula itself is discarding them. Now what about values in between? What about the number 0? Can I put 0 into the derivative?
No.
Why not?
Because it makes it undefined.
This is going to be an egg value.
I'll put 0 in right now. Negative 2 over negative 1. The answer is 2. What have I found? Have I found the slope of this thing at 0?
0. Oh, okay, never mind.
It's a semi-trick question.
Is this like you found the limit?
Hold on a second. I have the derivative now of original ln x plus 1 over x minus 1, right? That's what I have, the derivative. We said before, I should not be able to put 0 into the derivative. But the formula itself seems fine with it. I'll put 0 in, and I'll get negative 2 over negative 1, which is 2. So the slope of this curve here should be a rate of change of 2 versus 1 at the location x equals 0. So why not?
Isn't it because it doesn't fit in the original domain?
Yeah, because there is no function at 0. This thing doesn't exist at 0. There's no slope at 0. There's no function at 0. You know what I mean? There's no curve at 0. So there's no slope to be there. Even though it's okay to put it in this function, but the derivative is coming from that. So since it came from that, its domain can be no bigger than that. You know what I'm saying? Do you know what I'm saying or not? I think it's pretty straightforward, but I've taught this the past few times. Are you with me or not?
I get it.
There's no graph of this at 0. So there's no slope at 0, right?
And then you
You can only have a certain selection of numbers for x that are valid that you have to put in, right?
That's right. It's that original selection, the domain of this thing.
So 0 is disqualified even before.
It's just disqualified. That's right. Even before we see this result here, and it looks like the 0 is fine to go in here. It doesn't cause any problems in this expression, but this expression is based on a domain of an original function which 0 does not satisfy. So
Because it won't
the
give you
domain that you
the
started with, the domain you
correct
ended with, it cannot get bigger, right? There's no curve there. All right, good job. I want to do the same problem again.
See?
Yeah, not the same way though. That would be. Oh, that would be bad.
Good at meaning it like that.
Actually, it might be good for you. I don't know. Season? You may do it again the same way?
Yeah.
I'm just yes, season. All
Yeah,
right.
sure. Do it.
What was I going to do? Natural log of x plus 1 over x minus 1. Do you guys remember your log properties? You're going to want to. It's going to help you immensely in these sections and for the derivatives with logs, remember log properties. So I'm going to write them out now. We're going to use it on this one and come to a similar result, hopefully more quickly. So the three main results for
What number
logarithms.
is this?
Log properties.
So what number is this?
The same one, 9. And I'm just going to write out some log properties. And we're going to use one to solve this problem in a slightly more efficient manner, or I think it's more efficient. So log properties. Any log base b, doesn't matter. Log base b of x times y, of two things, is log bx plus log by. Okay? So if you have a product inside the logarithm, it becomes the sum of two logarithms. And each part of the product is in their respective logarithms. And there's a similar thing for a quotient inside, which is why I'm bringing this up. We have a quotient here. So log b of x over y is going to be a difference of logarithms. And then the last one is an exponent. Log b of x to the m equals m log of bx. An exponent on the inside becomes a coefficient outside. You guys remember those three properties of logs? Okay. So we can use the middle one here. I could rewrite our function as y equals ln x plus 1 minus ln x minus 1. And this will avoid the quotient rule we had to do before, right? And it almost avoids the chain rule. So now if I take the derivative dy dx of this expression, ln of x plus 1 should just be 1 over x plus 1. Now granted, it should be times the derivative of x plus 1, but that's just 1, right? Okay. 1 over, okay, anyway, minus derivative of ln x minus 1 is 1 over x minus 1 times the derivative of x minus 1, which is 1. So it's itself. Okay. So that expression, if we combine it into a single fraction like we have down there, then it would read, read what it has down there, x minus 1 minus x plus 1 over x plus 1 x minus 1. And the top just becomes negative 2. 2 plus 1. Same thing, okay? That's the more efficient way to go about it. Think about log properties initially in these problems.
How did you make it? Oh, it's just one.
Same cancellation we made over here, because you see it's the same basic expression, right? I mean, the numerator here is the same basic expression. The numerators are the same. In a problem like this, though, when you analyze the domain, you should analyze the original expression. You should not change it to any other state and then start analyzing the domain and claim that's the domain. It's not necessarily so. Always analyze it from its beginning. Okay? Domains can change when you start playing with these rules a little bit. All right, log.